So Bevy Jam is coming up next month, and I've decided to take one of the workshops that I normally put over on Rust Adventure over here on YouTube. This workshop in particular is about 45 minutes and builds the game Flappy Bird. It covers handling collision, building your first plugin, your first observer, and more introductory concepts. It also has a bonus section where you write your very first shader. So I hope you enjoy this, and if you're watching it in the future, I keep these workshops up to date with the latest Bevy over on Rust Adventure. With that, let's get you into Flappy Bird. To begin Flappy Bird, we'll want to start a new Bevy project. In our case, we're going to use a starter repository specifically prepared with the assets that we're going to use at Rust Adventure/Flappy Bird. You can clone the repository, download a zip from the website, or use one of the following tools like the Bevy CLI. The Bevy CLI is the quickest way to start a new Bevy project and provides some really nice benefits if you want to deploy your application to the web later. If you want to install it, check out the instructions in the repo. The Bevy CLI uses cargo generate behind the scenes to scaffold new projects, so we can use the starter project from the Rust Adventure organization in the Flappy Bird repo on the branch Bevy 0.18 starter using this command on screen. As always, any text I show you is also written down below this video, so you don't need to type this all out, you can copy it from the website. The very last Flappy Bird at the end of the command is the directory this project will be scaffolded into. The output should look something like this. If you don't want to install the Bevy CLI, you can instead use cargo, and cargo new will scaffold a new minimal example. You will have to pay a little bit closer attention to the rest of the code in this lesson if you use cargo new, since it will be a very minimal project and won't actually include Bevy as a dependency. If you used cargo, you will have to add Bevy explicitly. We're using 0.18, so we can do cargo add 0.18. In both cases, what you'll end up with is a new package named Flappy Bird, or whatever you named your directory, as well as a dependency on Bevy 0.18. Whether you choose the Bevy CLI or cargo, the project will end up looking similar. Source.main.rs is our bootstrapped application, which brings the Bevy prelude into scope, creates a new app, adds the default plugins to the app, and runs the game. The app run function will block the execution of the main function, which is the entry point to our binary. This will eventually return an app exit when the program finishes, such as when the user quits the game. A prelude is a fairly common concept in Rust. A prelude is a convention where the library authors tend to put 80% of the stuff you'll likely need to make it available to bring into scope at the same time. What is in the prelude for a particular project is up to the author of the project, so some preludes include everything and some projects don't even have preludes. Bevy's prelude includes most but not all of the structs and other tools you'll want to make use of in an average Bevy project, which we can bring into scope with use Bevy prelude star. The app type is a type we can use to set up a new Bevy application with custom plugins and systems. The style of API here is called a builder API, which lets us chain more and more configuration onto that app type. This is why we can call app new followed by app add plugins followed by app run. App new returns the new app with a default configuration, while add plugins returns an exclusive reference to app, which allows us to call more of the app functions. App run finishes the builder off and kickstarts the application. The add plugins function adds the default plugins to the application. Bevy has many features, and the default plugins is a group of plugins that will include or exclude other plugins based on which of the cargo features is enabled. This includes things like window management, 2D and 3D APIs, asset management, and more. If you used the Bevy CLI, the cargo.toml will have a number of configurations. The important part for us is the Bevy dependency. Pretty much everything else is optional, except for the top package lines, and serves to make the experience a bit nicer. Feel free to read through them all as they are all commented, and there's a link of course to the Git repo if you didn't use the Bevy CLI in the post below this video. Whether you use the template or cargo new, there should be a .gitignore file that contains a single entry, which is the target directory. The target directory is a place where build artifacts go, so we don't want to commit that to Git. If you're using the Bevy CLI, then you can use Bevy run to run the game now. Here's what the output looks like on an M1 Mac from about 5 years ago at this point. Notice that Bevy prints a number of diagnostics, including how much RAM your computer has, which GPU and backend are being used, and more. If you're still using cargo and not the Bevy CLI, you can also do cargo run at this point. Also note that running the game will create a cargo.lock, if Rust Analyzer hasn't done that for you already. This records the dependency configuration you used when you built the application. Feel free to take a look inside since it is just a TOML file and is human readable as you can see on screen here, and you can really choose to do what you want with this file. People typically commit these cargo.lock files to their repository when developing applications, but not when developing libraries. With a scaffolded running Bevy application, there's not much on screen. To be able to render anything, we need to spawn an entity with a camera component because cameras define what is in view and where to render the output. For example, a camera can use the window or an arbitrary image as a render target for what it actually can see. For every frame of our application, Bevy runs systems in groups called schedules, but not all schedules run every frame. One useful schedule that doesn't run every frame is the startup schedule. This schedule runs once when the app starts up for the very first time. This means we can add a system to the startup schedule to spawn a camera when the application starts up. We add systems to a schedule by taking advantage of the builder APIs on the app type. In this case, that's app add systems. This allows us to specify one or many systems to add to a given schedule. In this case, we're adding a system named startup to the startup schedule. Note the difference in capitalization here. One is capital S, which is representing the schedule type, and one is lowercase s, which is representing the function we defined. Our system can have any name, so feel free to play around and name it anything you want to. But the schedule name has to be specific. It is a type name, so has to be the capital S startup struct. But what are systems? A system can be a regular function, which is how we define our startup system. These systems can be added to any number of schedules, which controls when they'll run within each frame. There is a full listing of the main schedule documentation and all of the schedules inside of it that you can add systems to in the docs. Since systems are executed by Bevy, we also get to take advantage of dependency injection to ask Bevy to give us whatever data we need. The arguments of our function will be handed to each system as it runs, which is a core way that Bevy knows when to schedule systems relative to each other. Commands in this case is one of the injectable parameters, which we call system params. We can query the state of the world and many more using these system params. Commands in particular is how we create new items in the global Bevy world state, such as spawning new entities. So we've used command spawn to spawn a camera, and what we mean when we say spawn a camera is that we've created a new entity and added the camera component to it. Systems operate on this component data by querying it. So by adding the data to a live entity, systems inside Bevy that handle rendering our application will find the camera data and use it to perform the actual rendering. We can use another spawn call to create another entity with a sprite component. This will eventually represent our player's character using an image, but for now we're just blocking out the space. This sprite also gives us something on screen to be able to see, which helps confirm that we've spawned our camera incorrectly and that we are rendering this little sprite. When spawning the sprite, we take advantage of two new components, sprite and transform. Sprite is a component that contains useful information for rendering an image in a 2D environment. This is how we provide the necessary data to Bevy's rendering system. We also use transform, which provides data for positioning an entity in world space. Note that our transform is constructed from an x, y, and z value, and is three-dimensional even though we're working in 2D. You can treat the z value as similar to a z-index if you're familiar with that concept. This z value determines what layer a sprite will be on compared to other sprites, and thus whether it is in front of or behind another sprite. If you resize the window now, the size of the square box sprite we spawned in doesn't change. This is because making the window wider or narrower is showing more or less of the game's world space. It would be nice to have a deterministic size for our game so that we know when the window is resized, the sprites in our game will still be positioned where we want them. To do this, we can set the projection component's scaling mode. We're going to use a 16:9 aspect ratio that exactly scales to other common resolutions, which will be 480x270. This will match 1080p and 4K resolutions when multiplied by integers, which means if someone full screens our game on a typical monitor, we can expect it to scale well. 480x270 times 4 is 1920x1080, and 480x270 times 8 is 4K. The scaling mode we're using comes from Bevy Camera Scaling Mode. We have to change the use item bringing Bevy Prelude in to also bring in the scaling mode enum in the camera module. Then we'll use it in the projection component alongside our Camera2d. The projection component is an enum that would allow us to use perspective, orthographic, or custom projections for our camera, and the orthographic projection is what we get by default when using the Camera2d component. So we'll keep using that and set the max width and height to 480x270. For any fields we haven't set, we'll default to the default 2D value. This results in a larger square on screen even though we haven't changed the world space size. There are some other scaling mode variants other than Auto Max that can be used. which can be more or less appropriate in different circumstances. You might want to try fixed horizontal, for example. Currently, we only have a white square for our player. We'll change that to be a variation of the Bevy logo, since this is Flappy Bird and the Bevy logo is, well, birds. If you used the template at the beginning of the workshop, you will already have the assets directory with the assets we need inside of them at the root of your project. If you didn't, go get them now from the repository, which is also linked below on the website. These assets will include 3 PNG files, a background image that we'll use later, the Bevy Bird, which will be our player, and a pipe. We'll use the Bevy Bird PNG as the first asset, and we'll put it on the sprite we created earlier. Loading the file will require using the asset server. The asset server is stored in a resource that we can ask for in our systems. We'll use the asset server load function to load the Bevy Bird PNG. This function will not block our program while loading, but it will give us a handle to the asset that we can use with the sprite. A handle is an ID that we can use to identify specific assets after loading them. Use the image field with the handle returned from load to render the Bevy Bird. The load function takes a path that starts at the root of our assets directory, which means we don't need to use assets as a prefix. You can use Bevy Run to see the bird rendered in the application now. The Bevy Bird sprite is on screen, but it's not moving yet. The classic Flappy Bird applies gravity to the player constantly while letting the player jump, which moves the player in an arc. The player in our implementation won't move left to right. Instead, we'll position it offset from the left edge of the screen and move the pipes past it. This will make it look like the bird is moving forward through the level and make our player controller a bit simpler since we only have to deal with one axis of movement, the y-axis. We'll take care of gravity first by starting to create a set of new components. I typically place these near the top of a file, but the source code location largely doesn't matter from a functional perspective. We'll create a player component for labeling the player character, a gravity component for setting the gravity scale for an entity, and a velocity component for tracking the accumulated velocity for an entity. The player component allows us to differentiate the player entity from other entities when querying for data in our systems. It also requires the other 2 components, gravity and velocity. This is a Bevy feature called required components, which allows us to guarantee that if we insert the player component on an entity, then these other components will also get inserted as well. We also get the option to set default values that will be used when inserting these extra components. One way is to derive a default implementation for the component, which is what we do for velocity. And the default implementation for an F32 is 0, so our velocity component will get a value of velocity 0 when the player causes it to be inserted. Another option is to define the value in the require attribute. This is what we'll do for gravity, which allows us to set the gravity scale per entity and define a different value in any require attribute. Our gravity component will set the gravity to 1000 when inserted because of the player component. In general, when working with 2D, a value of 1 means 1 pixel, so a gravity of 1000 means 1000 pixels. In 3D, this is slightly different and 1 unit equals 1 meter, so you might see something more like 9.8 meters per second squared compared to our 1000 in 2D. This value at the end of the day is fairly arbitrary, and you should feel free to play with it. Add the player component to the entity with the Bevy sprite, which will now also cause the gravity and velocity components to be added. Now this is great, but it doesn't do anything just yet. Just having the data around doesn't have any impact on the sprite. So we need to build a gravity system. Using these new components, we can write a new system that queries for the relevant data and operates on it. To access the data in our game, we can treat the ECS as a kind of database and query for it. Using the query system param allows us to fetch the components that are on entities. Iterating over this query is equivalent to iterating over each entity's components in turn. In our case, we'll only have one entity in the query results, so we could use a similar query like single, but the logic here is generic and looping is not costly. Any entity with these components would behave in a similar way, so looping happens to make sense here. However, the mutability of the values is important. References, which are the ampersands, are generally required, and those can be shared or exclusive references. Exclusive references are written as ampersand MUT or mute, and allow us to mutate the values of the components, while shared references, which are just the ampersands, only allow us to view the values. Since we'll be mutating the components when we iterate over them, we'll also need mute declared in a few places, especially including the ampersand mute transforms variable that we'll be iterating over. The other system param we use is the time resource. Each frame using the time resource gives us access to how much time has passed via the delta secs function. This is short for delta seconds. This allows us to change the velocity over time by subtracting the gravity multiplied by the time. Then additionally calculate the change to the entity's transform by applying that velocity to it. This configuration will make the player accelerate downward over time. Our gravity calculation numbers are again relative to pixel counts, which is why we aren't using something realistic like 9.8, and rather something a little bit more like 1000. Feel free to experiment with alternative calculations at this point to see how it affects the player's movement. We also need to add this system to our app, for which we have two options. The system can run in the update schedule or the fixed update schedule. Either will work at first, especially if you're only ever running on a single computer and a single monitor. But the delta time in update is dependent on the frame rate, while fixed update will have a consistent delta time. Generally speaking, rendering logic goes in the update schedule, while gameplay logic and movement goes in the fixed update schedule. This helps ensure consistent behavior across frame rates and devices. We really don't want our bird moving faster or slower depending on whose computer it's running on. Now that the bird is falling, we also need a way to let the player make it go upward. This will be a stiff, jolting movement that would be similar to an instantaneous force in the upward direction. To handle this, we'll accept user input, and if a button is pressed, then we'll insert an arbitrary upward velocity. Add a controls system to the update schedule. We only have a single player, so we'll be taking advantage of single this time. This behaves similarly to query with the exception that it expects exactly one result. We'll query using single for the velocity component on the entity, and the second type argument filters for only the entities with that player component. There's only one entity with the player component, so this all works out. We'll also need access to the button input resource for mouse buttons. There are others we could use, such as keycode, which you might want to play with, but the important APIs are part of button input, which includes the function AnyJustPressed. We'll check to see if mouse button left or mouse button right were pressed in the current frame. If so, set the bird's velocity to 400, which will cause an upward jump when we press a mouse button. The gravity system then takes care of decreasing the velocity over time, causing the bird to fall and jump whenever we click our mouse. While the bird can now fall and move upward, it is quite annoying to have to quickly catch the bird as it falls way past the screen, especially if you're using a window manager like me, which automatically repositions windows. We'll implement a bounds check to make sure the bird falling past the canvas is considered a game over event, and an observer to respawn the bird in response. The first thing we'll do is a small refactor. We'll need to know certain values to do the work that we want to, like the size we chose for our canvas and the size we chose for the bird sprite. We'll extract these values from their usage locations and put them into a couple of constants at the top of the file. We can then replace our usage with these constants in the projection component as well as the sprite component. Our new bounds checking system can use these new constants as well, which is the entire point. Note that I've left in a commented out trigger here that we'll use soon. In the meantime, we'll use an info log to check to make sure our detection is working. Given that our canvas is centered at the center of the window and the edges are roughly half the canvas size in each direction, we can check the negative and positive bounds in each direction. We'll add or remove additional distance based on the size of the bird sprite. I've chosen to be a bit lenient to the player so that the top of the bird touching the top of the playing field doesn't result in a game over, but you can choose to modify this to be as strict as you'd like. We'll also add the check and bounds system alongside the gravity system in the fixed update schedule. When the game is run now and the bird passes outside of the canvas bounds, the new info log will be shown. This should happen for both below the screen bounds and above the screen bounds, and the log will continuously output as long as the player is outside of those bounds. Now that we have a bounds checking system in place, we can deal with what to do if the player does hit something. In this case, we'll choose something straightforward and stick to only respawning the player. Step 1 is to create an endgame event so that we can use it. I typically like to place these near the other components, near the top of the file, but if there's a lot of code, I also place them near the systems that use them. The triggered event won't be handled by the observer system until after the end of the system function it was actually triggered in. The reason for this is that we can't pause a function mid-execution, so these observer events are handled directly after the function ends. We'll also use the command system param to trigger the event, which we've used in the past to spawn in new entities. With the event written, you can uncomment the commands.trigger line that we added earlier. Observers are just like systems with the caveat that the very first parameter needs to be the event we're listening for. In this case, we don't care about the value of the endgame event, so we can prefix the name with an underscore. We can take advantage of commands and single again to get the other information we need. In this case, all we're really doing is repositioning the bird on screen, so reinserting the transform and velocity components will move the bird to the correct position and reset the velocity. The velocity value here is fairly arbitrary. I've set it to 0, so the bird will almost immediately start falling once gravity is applied, but putting the transform X position of the sprite 1/4 to the left of center was an intentional choice. This will keep the player on the left side of the screen as the pipes come towards them from the right. In the respawn on endgame system, we query for the entity itself because commands has a nifty function called commands entity, which lets us get access to an entity commands for that given entity. This allows us to take the same set of actions we can take when spawning a new entity, which means it allows us to insert components and perform other operations. Note that we've also moved the bird to the left like I talked about earlier. Specifically, it will respawn at 1/4 of the canvas width from the left. The value here is negative because we're offsetting it from the center of the screen. This will make it more obvious that the respawn is actually doing what we want it to, and also is where we want the bird to end up anyway. We finally need to add the observer to our application, which we can do with the app add observer function. After confirming that the player respawns on the left side of the stage, we can change our original spawn to also spawn in the correct X location in the first place. With a player character moving in the correct way, we'll need a set of pipes to move through. In Flappy Bird, the pipes move instead of the player on the X-axis, which allows an infinite playground of pipes to move through. This also makes it easier to sync the camera with the player's position. There's no actual camera movement in this game. The pipe functionality can be completely separate from the rest of our game since it's actually completely encapsulated. To emphasize this, we're going to build a plugin in lib.rs and then use that plugin in main.rs. Our first step is going to be to create the source lib.rs file and move the constants from main.rs into it. After removing the constants from main.rs, we'll need to re-import them back from our library. Instead of doing them one by one, we'll bring in anything that's public into scope using star. The library name here is the name from the cargo.toml by default. So in my case, that's Flappy_Bird, but if you named your project something else, it will be the name of the project that you chose. Similar to the way we can organize code into modules in Rust, we can use plugins in Bevy to encapsulate systems, resources, and other useful functionality. Plugin is a trait that we can implement, so we'll create a new pipe plugin struct and write the absolutely minimum to satisfy the trait. While the pipe plugin is a unit struct here with no fields, it could also hold configuration that we use in our plugin implementation. When we add this plugin to our Bevy application, the build function will get called, which will result in a log to the console, confirming that we've set our plugin up correctly. Back in source main.rs, we'll add our pipe plugin to our app. I personally tend to like separating my applications plugins from the upstream plugins or third-party plugins like default plugins. So I've used an additional add plugins call here, but you could use a tuple and a single add plugins call as well if you prefer. Running the application with cargo run should now show our log when the build function runs. Let's take a look at our pipe texture next by spawning it with a sprite. The actual image size here is 32 by 80 pixels. This is again one of the assets that came with the template that we used at the beginning of this workshop. So if you used the template, it should be in the assets directory. If you didn't, you're going to have to go get it from the Git repo now. We know we'll already have to spawn many pipes, so we'll start off immediately by adding a new spawn pipe system to fixed update in our pipe plugin. Normally this would run many times, but we can use a condition to make it only run once. This is a built-in condition and is called run once. These conditions are basically systems that return a boolean, which means internally run once keeps a bool that is set to true the first time the system is run and prevents running the system every time after that. This also means our spawn pipes system only has to care about how to spawn a pipe, and it doesn't have to deal with configuring itself to spawn at specific times. We'll use commands and asset server here as system params, which we've seen before in this workshop. Great, we'll need to scale the sprite vertically to get it to cover the screen, so let's double the size to check to see how that renders. By default, the sprite will use the image size, which as we covered before is 32 by 80. So let's keep the width at 32 and double the height to 160. The image stretches vertically, which is actually really unfortunate for the pixel art that this pipe is. We can fix that though using the image mode field on sprite. The sprite image mode sliced variant allows us to cut our image into 9 pieces, which is a 3x3 grid of tiles. We define the size of the corner tiles, which won't scale or stretch, and set the center tile to stretch. Since we aren't stretching the image widthwise right now, this will result in the center tile stretching vertically to fit the new size of the sprite, which is exactly what works really well for our image. Do note that the value 8 that I chose for the width in this case is pretty arbitrary and doesn't actually affect anything since we aren't currently changing the width of the image. Similarly, the value 19 is fairly arbitrary, but a little bit less so. In this case, it's the smallest number of pixels that contains the top of the pipe. These values are relative to the original image texture pixel size, so 32 by 80 in our case. The height looks good, but if we zoom in on the pipe top, we can see that the image is actually still pretty fuzzy. This is due to how images are filtered or sampled by the GPU when being displayed. In this case, the image is using linear filtering, which means the pixels are being combined in certain scenarios. This is not great for pixel art like our pipe, so we need to use nearest filtering instead. We can specify what kind of filtering we want when loading the image using the load with settings function and setting the appropriate value in those settings. In this case, we're using image loader settings because we're loading an image, so make sure you also bring that into scope at the top of the file. This fixes our blurry image. Note that specifying the filtering mode per image would get tiresome if you had a lot of pixel art assets, so you could set the default using the image plugin settings instead. I personally don't like the way this makes the bird asset look, so I didn't do that here. But with that, we have a properly sampled pipe spawning on screen that we can change the height of at will while keeping the visual we want. The reason we scaled up our pipes in the last lesson is so we can orient them above and below a center gap that the bird can fly through. We can build a hierarchy of entities to orient multiple sprites in different positions to build this gap. To do that, we'll use 4 new components in lib.rs: pipe, pipe top, pipe bottom, and point skate. We'll also add 2 new constants to determine both the pipe size and the gap between the 2 pipes, but contrary to our other 2 constants, these are only used locally in this file, so we don't need to make them public. The height of the pipe size is using the canvas size.y value, because this is an easy value which we will never exceed. All we're really trying to do here is make sure the pipe sprite is always tall enough to fill the rest of the screen, and there's no strong reason to do it dynamically by adjusting the height at runtime. The setup we're going for is a gap surrounded by 2 pipes vertically. Ideally, we want a single element to query for to move the entire hierarchy, and in the future we'll want access to the point skate and pipe elements as well. The component labels for pipe top and pipe bottom are going to be used in a later lesson when we implement collision detection. The command spawn function accepts a bundle of components. This bundle can make use of the children macro to indicate that a set of additional bundles should be spawned as children of the current entity. In this case, we have a root entity with transform and pipe components with 3 child entities. The hierarchy looks something like this, with the root entity having the pipe and transform components, and 3 children, the first of which has a pipe top, transform, and sprite, the second of which has a point skate, a transform, and a sprite, and the third of which has pipe bottom, transform, and sprite. And the code to spawn it goes right in our spawn pipes system in lib.rs. In this code, the transform variable will control where the pipe is on the x-axis as we move it, and gap y position will control the height at which the gap is centered. It's also notable that if you forget the visibility component on the root entity, you'll see some warnings. This is because we have children with sprites that need to be rendered, but our root element doesn't have anything like that on it. The visibility propagates down the hierarchy, so a missing visibility component on a node in the middle of a tree can cause issues. We also reuse the image and image mode values twice, once for each pipe, which is why we clone the first usage of each, so that we have 2 copies to use. Cloning a handle to an image is extremely lightweight, since the handle data that it references is actually behind an arc. Arcs are a little bit more of an intermediate to advanced Rust concept, but cloning them increments a counter instead of copying old data. Bevy's transform is at the center of the entity they're placed on, by default. As a result, sprites are centered on their entity's transform translation, and a child's transform defines an offset from their parent's transform. The pipe offset then is half the size of the gap plus half the size of the pipe sprite, which offsets the pipe sprite's center away from the center of our pipe root entity. Due to how we set up these entities in our hierarchy, moving the pipes becomes a query for the pipe's transform and the time resource. We only need to move the root transform because everything that is a child will move with it. The time resource will give us exactly how much time has passed since the last frame. We'll run this system in fixed update since it's gameplay related, and this is an important point because using fixed update will mean the pipe speed isn't dependent on the frame rate of the person playing the game. We iterate over all of the transforms for any pipes that were spawned, and move their x coordinate left by the pipe speed constant amount according to how much time has passed. Then back up in our pipe plugin, we'll add the shift pipes to the left system in our fixed update schedule. While we're up here, we'll also need to create the pipe speed constant that we haven't created yet. We can also take this opportunity to change the run once condition to a timer that spawns a pipe every 1 second. Doing this will require bringing in duration, which lets us define the time, and on timer, which is a condition that Bevy provides. There are still 2 changes we need to make to the pipes. We need to despawn them when they leave the field of play, and spawn pipes to the right of the field of play out of view. To understand that our pipes aren't despawning, you can take a variety of actions, including writing a system that queries for entities with a pipe component and counting the results, making the camera show more of the world space and visually checking, or a number of other approaches. There are also popular inspectors in the ecosystem that you can install to visually inspect the entities and components in your application, but we won't cover them here. For this project, you can either use one of the aforementioned solutions to verify that the system is working as intended. Our despawn system queries for entities with a transform and a pipe component. In this case, the query will fetch the entity ID and the transform component value when we iterate over it, but not fetch the pipe component. We use the transform to check if the pipe has left the field, and if it has, use commands entity to get access to the entity commands for this entity. The despawn function is the one we're looking for, since that will despawn the entity and remove its components. This also happens recursively, so if we despawn the root entity, it will despawn the root entity, all children, and all of their components. Don't forget to add this system to our set of systems, or of course it won't run. We should also make the change that will spawn pipes to the right of the playing field. In spawn pipes, change the pipe transform variable to use a value that is at least half the canvas X size as the X value. And with that, we have a player-controlled bird and moving pipes. There are 3 entities that the player can collide with: the top pipe, the bottom pipe, and the gap in between the pipes. If the player collides with a pipe, their game is over and should reset or respawn. If the player collides with the gap entity, it should despawn, and the player should earn a point. Flappy Bird is a game with fairly lightweight collision needs. For boxes, we'll use the AABB2D struct, and for circles, we'll use bounding circle. Both of these types are regular structs that can be created for very little cost on the fly every frame. And AABB2D has a new function that accepts an XY position in the world and the half size of the box. The half size is very important and is slightly different than the way that we define, say, the custom size on a sprite. It is, however, exactly what it says, half the size of the box it refers to. That leaves us with roughly this logic for creating new AABB2Ds, which takes our sprite's custom size and divides it by 2. The bounding circle is the same, but accepts a radius in the second argument instead. And so far, we've been working with the transform component, but there's something worth knowing about how it works. A transform represents a local position offset from the entity's parent position. A global transform represents the entity's position in global space. At the very end of the frame, transforms are accumulated through the tree of entities that exist, and these values are stored in the global transform. We actually want this global position value and need it to be up to date to do our collision detection. But since the global transform is only updated at the end of the frame, we have 2 choices. We can either live with being a frame behind, or we can accept the performance cost of updating any entity's global transform right when we need it. In this workshop, we're building Flappy Bird, so the cost of computing the global transform again is very acceptable, and that's what we'll do. That is done using the transform helper system param and its compute global transform method. With the right positions and the constructed collider types, we can take advantage of the bounding circle and AABB2D implementations of the intersects volume trait. Concretely, this means we can call .intersects on any 2 relevant values. With all that background, we can see the system that will compute our collisions. There's quite a few new topics here, so take some time to read through it on the website if you need to, and we'll continue talking about it line by line. We've seen commands and single before, So or is the first new item. Or with the widths inside of it will match any entity that has either pipe top or pipe bottom. All pipes collide the same to us, so we use this query to group them all together. Gizmos are also new. Given that we're working with what are effectively invisible colliders, it can be useful to visualize where the colliders would be. This is where gizmos come in. Every frame, if we call the gizmo functions, a shape will draw on the screen that frame. Gizmos can be turned on and off using a bit of configuration. For example, this bit of code added to our startup system will control whether gizmos render or not. Gizmos work like this because you can create your own gizmo groups for specific purposes and enable or disable them as an entire group. This is what crates like avian physics do for their more complicated gizmos. The transform helper is how we'll force the global transforms to be up to date when we need them to be. The pattern for all of the colliders is the same. Get the up-to-date global transform, build the relevant collider struct, and draw the gizmo to show the collider. With our check collision system, we need to add it to the fixed update alongside our other systems with one major caveat. The check collision system needs to run after the gravity system if we want our gizmos to draw the effects that the gravity system had on the transform every frame. To order our systems, we take the easy path here and use .chain on the tuple. This ensures that all systems in a tuple run in order. Note that we also have a host of new items in scope for our collisions, including AABB2D, bounding circle, and intersects volume. Running the application now will show the circle collider around the Bevy Bird, as well as the colliders for each of the pipes. The last critical piece of Flappy Bird is keeping score. We already have the collision in place, so what we need to do is respond to the collision by triggering an event, and respond to the event by updating a score. We'll keep that score in a global resource and create a new event as well as a marker component to label the text that will display the score. Resources need to be initialized or added to the world before the systems that access them. So we need to initialize score using its default implementation at the beginning of our app's lifecycle. We use a init resource to do this. In our collision system, we test for the intersection of the player with any gap, and we output a log before despawning the gap. We'll change that log to trigger an event instead. And we'll add an observer to listen to the event. This observer will add 1 to the score resource whenever it's triggered. And now that there is a score resource that increases every time the player scores a point, we need to actually show that to the player so that they know. To do that, we'll spawn a new text component with a default value. I gave the text some colors and centered it in the node using justify center, but feel free to put it wherever you want to. Updating the score requires querying for that text component, which we labeled with score text, and updating it with the stringified value from the score resource. I use a for loop here because it's a bit more forward thinking. If we add a second place to render the current score in the future, this system will just continue to work with that location as well. Finally, we want to run the score update system whenever the score resource changes instead of every frame, which we can do with a run if resource changed and passing in the type of the resource. The final piece is resetting the score when the endgame event is handled. We do this by setting the score resource to 0 in respawn on endgame. And now we can play the game and score will be kept and displayed to the user. Next, we've got a bit of extra fun. It would be really nice to have a background for these pipes. The absolutely most straightforward way to put a background on screen is to spawn a sprite. Here I've used the asset server to load the background color grass PNG that was in the templates assets folder. The background image is a 1024 by 1024 pixel square from a Kenny asset pack, so I set the size of the image to be the width and height of our predetermined canvas size.x. There is one big problem here though, the bird is barely visible against our nice new background. We can fix this by adjusting the color of the bird's sprite. The code shown here parses a hex color into an sRGBA, which could fail theoretically, so we unwrap. The only way this would fail is if we mistyped the hex code, so unwrapping is fine here. The code also then uses into to turn it into the color the sprite color field expects. This is possible because both types are well known. The first is an sRGBA, and the second is color, And as it turns out, all color does is wrap sRGBA. That looks much better, but if you want to dig into shaders, we can go a little bit further without much effort. We'll need a few new items in scope, specifically image address mode, as bind group, shader ref, image loader settings, Camera2d, and Camera2d plugin. Here's the new use section. Firstly, we'll create a new struct with a few derivs on it. The TLDR here is that we're defining a new type of asset that will be used to define the data that gets passed to our shader. Then we implement Camera2d for that type, which defines what shader will be executed. We'll write the WGSL file last here. We still need to add the Camera2d plugin to our app to set up the new material as well. And in startup, add two parameters that request the mesh assets and the background material assets databases. We replace our sprite background with a mesh 2D and the new material we defined, which will apply our shader. We also set the sampler to repeat the texture if we sample a coordinate outside of the texture's bounds, which will be important in a minute when we write our WGSL file. The background.wgsl file gets created in our assets directory. We define a couple of imports which notably bring in the vertex output and globals, and we are writing a fragment shader, so we receive the data from the vertex shader that ran before us, as well as the data we defined in our struct. Globals is where we'll get the time, which allows us to scroll like background texture over time, and then we have two bindings. The group and binding numbers are literally indices in a vec. If you get deeper into writing shaders, you will end up seeing and writing the literal vec that these are defined in. But for our use case, we never see that vec here. And they're the numbers we chose when we defined our material. One of the bindings is the background image we loaded, and the other is the sampler, which defines how we access that texture. Remember that nearest configuration we used earlier in the workshop for our pixel art? That's literally defining how this sampler behaves when we sample pixels from the texture. Finally, we actually execute a texture sample. We pass in the texture we loaded, the sampler, and a set of coordinates which pick the location in the texture to sample from. This is where the magic happens. We use the UV coordinates of our mesh 2D, which are 0 to 1 values from edge to edge, and we move those coordinates over time using a time value scaled down by 10. This results in the 0 to 1 value that we're using to sample from the texture increasing each frame. Because we've configured the sampler to repeat if it goes above 0 to 1, the pixels of our texture will repeat from 1 to 2, 2 to 3, and so on. And that's it, you now have a scrolling background image that gives a parallax effect compared to the pipes. Let's also change the score text to the Bevy dark color while we're here. And that's about it for Flappy Bird. Let's finish off the application. We can turn the gizmos off if you haven't already in the startup system, using the default gizmo config group. And then we can make the gap invisible by setting visibility hidden on that entity. This removes the gizmo visuals, which we don't really want in our final game, as well as the block that used to be in the pipe gap. The entity is still there, it's just not rendering anything. However, the pipes in Flappy Bird are supposed to be in different positions. This can be accomplished more effectively using noise, but we'll start off with just a sine wave. In spawn pipes, add the time resource, and we'll use it to produce a sine wave. I multiply it here by an arbitrary number so that the output doesn't look exactly like a periodic sine wave, but there's a lot more work that could be done for choosing the locations here. The sine function returns a value between -1 and 1, so multiplying that by a quarter of our canvas size height means it will move up and down a total of half the size of the canvas. These numbers are all fairly arbitrary, so feel free to choose different numbers or combine multiple sine waves and do other things, like experiment with noise library. Our bird doesn't really move much here either, and we can add a little life by having it point in the direction of the arc it is following. Our pretend horizontal speed is pipe speed, and our vertical speed is the velocity value. Make pipe speed public so we can use it in main.rs, and then we'll use that value in a new enforce bird direction system. This system takes advantage of the fact that the angle of a 2D vector is just that vector. So since our x and y speeds are already relative to our bird, we consider the bird to be the velocity vector's local vec0. Since our calculated velocity -0 is just the calculated velocity, we can take advantage of Glam's vec2 2-angle function and make that a rotation around the z-axis, which is the one coming out of our screen. Since this system is only visual and not gameplay related, in fact it's even rendering related, we can put it into the update schedule. With this, Flappy Bird is done. The bird faces up and down, we have a nice parallax background effect, the pipes are in different positions, and collision has been enabled. There's more stuff you could do, like place pickups throughout the level, or extend the application in different ways. I hope you enjoyed building Flappy Bird, and I'll see you in the next workshop. And that's it for Flappy Bird. I hope you enjoyed it, and if you did, there's more workshops like this over on Rust Adventure. A subscription to Rust Adventure does also help fund this channel. And we don't just have Bevy workshops, it's also other Rust concepts. I hope to see you in the Bevy Jam next month, and of course I'll make more videos leading up to it. Have a great rest of your day.